So a previous notebook looked at F770 data, which has typically very low backgrounds. Not all of the MIRI data does this. The longer wavelength images, F2100, F2550, can have very high backgrounds. So I think the typical background for a 770W image would be maybe 5 megajanskis per steradian. At 2550, we're getting up to 800 to 900 megajanskis per steradian. So if you're trying to find faint objects within those images, you're not going to be able to see it very well with such a high background. So we want to do a background subtraction of those files to get down to the noise levels and see the fainter objects. There are also cases where we have some detector artifacts. We have something called tree rings. We have residual noise patterns, and you might want to do a sky background to get rid of some of those. Now, the code we're going to be looking at has been created by Carl Gordon on the MIRI team, and he has all of this stored on a GitHub repo, so you can go there to get the code and see other examples of how this is done. There is a very strong caveat on this method, however. It is best used when you have a field of stars without extended sources like galaxy or nebula emission that stretches across the image. The method we're doing is a simple stack, median, and subtract. So it's a very simple method. There are more complex methods that can be used. I don't happen to have those on hand. Also, the more dithers you have, the better this is going to work because you have a larger stack of images to start from. So the notebook will be showing this method on F2100 data. So again, if you're going to do this, the packages that you would need to be installed are JWST regions in Jupyter. You would run to download your data and set up your environment. I'm going to scroll through this because this is mostly the same thing that we saw before. So we'll set up our parameters. The helper scripts that do the sky creation and subtraction. So there are some parameters that need to be set. And in this case, I basically set everything to the null possibility. So scale background, we're not going to do this, as noted, experimental options for additional exclusion using DS9 regions. That's something Carl was working on. I did not work on that myself. And then just also, I'm not rotating the image. So basically, the parameters the code needs are set to their null values. This make sky has, again, a lot of different options, but the main thing that it's doing is taking all the images that was fed to it, stacking them at the different dither positions so that none of the point sources line up on top of each other. That's the important part of this. And then doing a median, and then subtracting that median sky from each individual file, and then outputting the sky subtracted files. In this case, we'll be working on the cal.fits files. So that will be the input, and we'll get a sky sub cal file at the out. There are a couple of other helper scripts, show image and overlay catalog. So we will take in our input files. In this case, we have 4 files, and I'm reading in the automatic masked output combined file for reference down the line. And take a look at them, see they are F2100 files, 1 integration, and 20 frames. And you can already notice there are some differences in what this image looks like compared to the one we saw previously. This is the last frame in the extension, or in the integration. So there's a high background level. You only see a few of the fuzzier point sources, and then some faint stuff that are probably galaxies. But you can see it kind of fades into the background. We run CalWeb detector 1, setting similar parameters. In this case, we're not going to do the fine showers because as you get to longer wavelengths, that sometimes gets a little tricky. So we're going to skip the showers this time. Scroll through all of the output. And then we'll take a look at our rate image. Again, looking at the do not use pixels. So you see the same shorted column, the same bad pixel areas. However, you've probably noticed that this rate image Has some spatial variations in the background. We've got some darker regions and lighter regions. We've got some noise patterns up here. And this is also another reason why we'll probably want to do a background subtraction to get rid of all these stuff. Run CalWeb Detector 2 and see if any of that has disappeared in the Cal image. Okay, so this is the point at which we will do our create and subtract the mean sky background. So this is mostly for file naming. You give it the filter name, give it the list of cal files, and this is just handy syntax to get your list of rate files now says cal instead of rate. So it's the full list of the cal files. You read that into the make sky parameter, or the make sky code, which then will take in all of your files, create the median background, and output the sky subtracted cal files. So here's the image beforehand. So this is our cal file before the background subtraction, which has gotten rid of some of the noise, so the flat fielding did its job. See the background, and then the sky subtracted background. This may look very noisy compared to the previous one, but it just means we're actually down in the noise levels, and all of these faint objects that were blending into the background previously are popping out, just visible all over the place where they hadn't been before. You can see this is also, we're not going to have the same number of point sources in this image that we did in our previous one. Because as you get to the longer wavelengths, you lose your point sources, or at least a good number of them. So then we again create our association table. And in this case, I did just set the parameters within the same block of code. Call your pipeline. And then we take a look at the final MIRI combined mosaic. So it's a pretty smooth background over most of the image, except of course the edges. And then we can compare our subtracted combined image to what came out of the pipeline with doing none of this. So if we don't subtract the background, if we don't adjust the parameters, this is what you get out of the pipeline. And you can still see the sources, but some of the fainter ones tend to blend in. We're getting these tree rings that I mentioned, so that's the detector effect. And then we have some noise up here where the combination was happening at the image edges. So you can see we have a vast improvement over, and that's also, this image has a background of about 200 something, whereas here our max values are about 2. So we're looking at this between 0 and 2. So that's the reason you want to do something like a background subtraction, especially at the longer wavelengths.